On a clear autumn night, far from city lights, you can see something impossible with your naked eyes. It's a faint smudge in the constellation Andromeda, barely noticeable unless you know exactly where to look. Most people miss it completely, dismissing it as a trick of tired eyes or a passing cloud. But that faint blur? It's 2.5 million years old. The light you're seeing left that object when our earliest ancestors, Homo habilis, first picked up stone tools on the plains of Africa. While those ancient humans were learning to shape rocks into blades, the photons now entering your eyes were already racing through the void of space at 671 million miles per hour. And here's what makes this truly staggering. That faint smudge spans 6 times the width of the full moon in your sky. If your eyes could see just slightly better, if that object glowed just a bit brighter, it would dominate the entire night sky like a cosmic rainbow stretching from horizon to horizon. It would be impossible to miss the most spectacular sight in the heavens. That object is the Andromeda galaxy, 1 trillion stars, 220,000 light-years across, our closest galactic neighbour and our cosmic twin. But in 2025, scientists just discovered something that changes everything we thought we knew. Andromeda isn't just sitting out there in space, it's moving towards us at 223,694 miles per hour, and the collision everyone predicted for billions of years? New simulations from June 2025 just revealed that the odds of it actually happening are only 50%, a coin flip. Our galaxy's fate hangs in the balance of uncertainties, so small they're measured in millionths of an arcsecond. But wait, there's more. In January 2025, the Hubble Space Telescope released the most detailed portrait of Andromeda ever created. Over 600 separate images, 2.5 billion pixels, more than 10 years of work, and what it revealed shocked astronomers. Andromeda has a chaotic, violent past completely unlike our own Milky Way. It's not the gentle giant we thought. It's a galactic cannibal that's devoured at least a dozen smaller galaxies, and it's still feeding. And just last month, in February 2025, astronomers discovered a new dwarf galaxy they're calling Pegasus 7. It's one of the faintest galaxies ever detected, 10 billion years old, and it's just now entering Andromeda's gravitational pull. We're watching, in real time, as Andromeda prepares to consume another victim. This is the story of Andromeda, a galaxy that might be our destroyer or might pass us by. A trillion-star empire with secrets we're only beginning to unravel. A cosmic neighbour that could reshape our entire corner of the universe or leave us completely untouched. We're going on an extraordinary journey across 2.5 million light-years. We'll witness stars being born, explore Andromeda's violent past, confront its supermassive black hole, and examine whether our galaxies will actually collide. Every fact is verified against the latest 2025 research. This is the cutting edge of what we know about our galactic neighbour. If you're ready to dive in, hit that like button, it helps others discover this, and subscribe for more deep dives into the cosmos. Now, let's begin. 100 years ago, in January 1925, an astronomer named Edwin Hubble stood before the American Astronomical Society and announced something that would shatter humanity's understanding of the cosmos. But the secret had already leaked. The New York Times had run the story 2 months earlier, and by the time of the official announcement, the world was buzzing. What Hubble revealed was simple but devastating. The Andromeda Nebula wasn't a nebula at all. It wasn't a cloud of gas inside our Milky Way. It was an entirely separate galaxy, an island universe, and it was 2.5 million light-years away. Overnight, the universe became infinitely larger. For centuries, humans had believed the Milky Way was everything, the entire cosmos, every star, every planet, every cloud of gas, all contained within our single galaxy. The idea that there might be other galaxies, other stellar islands scattered through an inconceivably vast universe, seemed almost absurd, but the debate had been raging for years. In 1920, 2 brilliant astronomers, Harlow Shapley and Heber Curtis, faced off in what's now called the Great Debate. The question, what were these mysterious spiral nebulae that telescopes kept finding? Were they inside the Milky Way, as Shapley argued, Or were they separate galaxies, as Curtis insisted? Shapley had measured the Milky Way and found it to be enormous, about 300,000 light-years across by his estimate. If Andromeda lay outside such a vast galaxy, it would have to be millions of light-years away. The distances seemed impossible. Curtis had a different argument. He'd noticed something strange. Novae, exploding stars, appeared much dimmer in Andromeda than in the Milky Way. If they were the same type of events, the only explanation was that Andromeda was vastly farther away than anyone thought. He also pointed to Andromeda's beautiful spiral structure. Why would a simple gas cloud have such organized, sweeping arms? The great debate ended without a clear winner. Both men presented compelling evidence. But the answer was already waiting in the data, hidden in the pulsing light of special stars called Cepheid variables. Cepheid variables are extraordinary objects. They pulse in a steady rhythm, brightening and dimming over days or weeks. And here's the magic. Astronomer Henrietta Swan Leavitt had discovered that the longer a Cepheid's pulsation period, the brighter it actually is. This created a cosmic yardstick. Measure how fast a Cepheid pulses, calculate its true brightness, compare that to how bright it appears from Earth, and you can calculate its distance with remarkable precision. Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, the most powerful telescope in the world at the time, began photographing Andromeda night after night. And there, buried in the galaxy's spiral arms, he found them, Cepheid variables, pulsing, measurable, perfect cosmic distance markers. When Hubble did the math, the result was staggering. Andromeda was 900,000 light-years away by his initial calculation. Later refinements pushed that number to over 2 million light-years. It was incomprehensibly far, so distant that the light Hubble was observing had left Andromeda long before humans walked the Earth. Curtis was right. Andromeda was a separate galaxy. And if one spiral nebula was actually a distant galaxy, then likely all of them were. The universe wasn't a single galaxy. It was billions of galaxies, each one an empire of stars, scattered across unimaginable distances. The announcement transformed astronomy forever. Suddenly, cosmology wasn't just about studying the Milky Way. It was about understanding the entire universe. How many galaxies existed? How far apart were they? How did they form? Did they move? Were they all the same? Or were there different types? And most importantly, if Andromeda was our nearest large galactic neighbour, what could it tell us about ourselves? For the next century, Andromeda would become one of the most studied objects in the sky. Astronomer after astronomer would turn their telescopes toward that faint smudge, seeking answers to questions that multiplied with every observation. But even Edwin Hubble, brilliant as he was, couldn't have imagined what we'd eventually discover. He couldn't have known about the supermassive black hole lurking at Andromeda's core. He couldn't have predicted the galaxy's violent, cannibalistic past. He couldn't have seen the simulations showing our two galaxies might collide or might miss entirely. And he couldn't have guessed that one day, in 2025, we'd create a photographic mosaic of Andromeda containing 2.5 billion pixels, revealing over 200 million individual stars. The great debate was settled, the universe expanded, and Andromeda became our window into understanding galaxies themselves. But the real journey was only beginning. In January 2025, exactly 100 years after Edwin Hubble's announcement, NASA released something extraordinary. The most comprehensive survey of Andromeda ever created. A photographic mosaic so detailed, so vast, that it took over a decade to complete. 600 separate exposures, more than 1,000 Hubble Space Telescope orbits, 2.5 billion pixels. And the result? An image revealing over 200 million individual stars, each one resolved, each one a sun in its own right, many of them possibly hosting their own planetary systems. But here's the staggering part, that 200 million stars represents less than 1/5 of Andromeda's total population. The galaxy contains an estimated 1 trillion stars. We've captured just a fraction, but that fraction alone is enough to revolutionize our understanding. The project had 2 phases. First came PHAT, the panchromatic Hubble Andromeda Treasury, which photographed the northern half of the galaxy over several years. Then came PAST, the panchromatic Hubble-Andromeda Southern Treasury, which completed the southern regions. Together, they cover the entire visible disk of the galaxy, creating a portrait unlike anything humanity has ever achieved. Why does this matter? Because for the first time, astronomers can see Andromeda's individual stars. They can measure their ages, their chemical compositions, their masses. They can trace stellar populations across the galaxy and reconstruct its history. Every star is a clue, a fossil record of ancient events, and with 200 million clues, the story of Andromeda begins to emerge. What that story reveals is shocking. Andromeda is not like the Milky Way, not even close. While both galaxies formed around the same time, roughly 13 billion years ago, in the aftermath of the Big Bang, they've had completely different lives. The Milky Way has grown steadily, absorbing smaller satellite galaxies over billions of years in a relatively calm, orderly fashion. Andromeda is a violent, chaotic survivor. The Hubble images show coherent streams of stars, long arcs stretching across the galaxy's outer regions. These aren't natural features of a peaceful spiral, they're scars, remnants of smaller galaxies that Andromeda tore apart and consumed. Each stream traces the death throes of a dwarf galaxy that ventured too close and paid the ultimate price. Astronomers have identified at least a dozen such merger events in Andromeda's past. Some happened billions of years ago. Their stellar streams now spread so thin they're barely detectable. Others are more recent. Their stars still clump together in recognizable structures. And some are happening right now. Take Messier 32, or M32, one of Andromeda's most visible satellite galaxies. It's a compact elliptical galaxy, incredibly dense, orbiting close to Andromeda's core. But M32 is far too small for its density. Computer simulations suggest it was once much larger, possibly a spiral galaxy in its own right. Then it made the fatal mistake of getting too close to Andromeda. Tidal forces ripped away its outer layers, stripping off stars and gas, leaving only the dense core behind. M32 is a ghost, the compressed remnant of what was once a much grander system, and this process continues. In February 2025, astronomers announced the discovery of Pegasus 7, a previously unknown dwarf galaxy located 2.4 million light-years away. It's one of the faintest Andromeda satellites ever detected, with a stellar mass of only 26,000 solar masses. For comparison, that makes it 5 times larger than the biggest globular clusters in Andromeda, but still minuscule by galactic standards. Pegasus 7 is ancient, roughly 10 billion years old. It's survived since the early universe, largely unchanged, drifting through intergalactic space, but now it's entering Andromeda's gravitational domain. Over the next few billion years, it will spiral inward. Andromeda's gravity will stretch it, deform it, tear it apart. Its stars will be scattered across Andromeda's halo, becoming part of the larger galaxy's stellar population. Pegasus 7 will die, and Andromeda will grow. This is how large galaxies form. Not through gradual star formation alone, but through galactic cannibalism. Andromeda has been eating its neighbours for billions of years. The beautiful spiral structure we see today is built, in part, from the corpses of dozens of smaller galaxies. But the Hubble survey revealed something even more surprising. Andromeda is more populated with younger stars than the Milky Way. Despite being older and more massive, it's forming stars at a higher rate in certain regions. The galaxy has vibrant blue star-forming regions scattered through its spiral arms, places where new stars are being born at an impressive pace. This suggests Andromeda has had a more active recent history than we realized. Each time it absorbed a smaller galaxy, the collision brought in fresh gas and dust. That material didn't just add to Andromeda's mass, it triggered new waves of star formation, creating bursts of stellar birth that continue to this day. The chemical analysis reveals even more. The stars in Andromeda's core, the oldest stars in the galaxy, have lower metallicity. That means they contain fewer heavy elements like carbon, oxygen, and iron. These stars formed when the universe was younger, before multiple generations of stellar death had seeded space with heavy elements. But stars in the spiral arms, especially in the southern regions mapped by PHAST, show higher metallicity. They're enriched by supernova explosions, by the deaths of massive stars that forged heavy elements in their cores and scattered them into space. These younger stars inherited a chemically richer environment, giving them compositions more like our own Sun. And here's where it gets really interesting. Some regions of Andromeda show unusual chemical signatures that don't match the main galaxy. These are likely remnants from absorbed galaxies. They're unique chemical fingerprints, preserved even after their stars scattered. Each conquered galaxy brought its own history, its own stellar population, its own chemical identity, and all of that is now mixed into Andromeda's vast stellar population. Looking at the Hubble mosaic, zooming into regions rich with individual stars, it's easy to forget the scale. Each tiny point of light is a sun. Many are. Larger than our sun, some smaller. Each burns with nuclear fire, converting hydrogen into helium, generating energy that streams into space. And surrounding many of them, invisible at this distance, are likely planets. Rocky worlds, gas giants, ice worlds, maybe even habitable planets where liquid water flows and complex chemistry might spark into life. If we assume Andromeda has a similar planet-to-star ratio as the Milky Way, then somewhere in that galaxy are trillions of planets. Worlds we'll never see, never explore, never know. Some orbit comfortably in their star's habitable zone. Others are frozen wastelands or scorched hellscapes. Some might have atmospheres thick with clouds, surfaces covered in oceans, continents shaped by geological forces, and on some tiny, statistically inevitable fraction of those worlds, could life exist? Could there be organisms swimming in alien seas, crawling through strange forests, perhaps even looking up at their own night sky and wondering about the faint smudge they call the Milky Way? We don't know. We may never know. Andromeda is simply too far. Even our most powerful telescopes can't resolve individual planets around its stars. The best we can do is wonder, imagine, and recognize that in a galaxy of 1 trillion stars, the odds of being alone seem vanishingly small. But the Hubble survey did more than reveal stars. It gave astronomers a tool to peer into Andromeda's past and predict its future. By mapping the ages and movements of stars across the galaxy, researchers can reconstruct its history. They can identify when major mergers occurred. They can trace the flow of gas that triggered starbursts. They can see how the galaxy evolved from a small collection of stars billions of years ago into the massive spiral we see today. And they can do something else. They can compare Andromeda to the Milky Way and ask, why are these two galaxies, born around the same time in the same cosmic neighborhood, so different? The answer is still emerging, but it seems to come down to history. The Milky Way grew more slowly, more steadily. Andromeda grew violently, through repeated collisions and mergers. Both paths led to large spiral galaxies, but the details of their structures, their star formation rates, their chemical compositions, all reflect their different pasts. And now, as we look toward the future, we have to ask, what happens when two galaxies with such different histories finally meet? Because they are meeting. Andromeda is moving toward us. And the collision everyone thought was inevitable? The latest simulations just changed everything. For decades, one thing seemed as certain as death and taxes. The Milky Way and Andromeda were on a collision course. Astronomers had calculated the trajectories, run the simulations, made the predictions. In roughly 4 to 5 billion years, our two galaxies would smash together in a cosmic train wreck that would reshape our entire corner of the universe. The story was dramatic, inevitable, almost poetic. Two galactic titans, each containing hundreds of billions of stars, spiraling toward each other through the void. The collision would trigger massive bursts of star formation as gas clouds compressed. Stars would be flung into new orbits, some ejected entirely into intergalactic space. The beautiful spiral structures of both galaxies would be destroyed, replaced by a single giant elliptical galaxy that astronomers had already named Milkomeda. Our Sun, if it survived that long, would likely be thrown to the outer suburbs of the merged galaxy, 3 times farther from the galactic center than it is now. Or it might be ejected completely, doomed to wander the dark space between galaxies for eternity. The collision was our fate, It was written in the stars. But then came June 2nd, 2025, and everything changed. A team of astronomers from the University of Helsinki, Durham University, and the University of Toulouse published a study in Nature Astronomy that shook the astronomical community. Using the latest data from the Hubble Space Telescope and the European Space Agency's Gaia spacecraft, they ran 100,000 computer simulations of how the Milky Way and Andromeda will evolve over the next 10 billion years. The result? The collision is no longer certain. In fact, there's only about a 50% chance it will happen at all in the next 10 billion years. 50%. A coin flip. Our galaxy's fate reduced to even odds. Dr. Til Sawala, the lead author from the University of Helsinki, explained the shocking conclusion. Even using the latest and most precise observational data available, the future of the local group is uncertain. We find an almost equal probability for the widely publicized merger scenario, or conversely, an alternative one where the Milky Way and Andromeda survive unscathed. How did we get this so wrong? How did decades of predictions suddenly become uncertain? The answer lies in understanding just how difficult it is to predict galactic motions over billions of years. Think about it. Andromeda is 2.5 million light-years away. To predict whether it will collide with us, we need to know three things with incredible precision: its current position, its current velocity in 3 dimensions, and its mass, plus the masses and motions of every other significant galaxy in our cosmic neighborhood. Let's start with velocity. Measuring how fast Andromeda is moving toward us is relatively straightforward. We can use the Doppler shift of its light, the same principle that makes an ambulance siren change pitch as it passes you. Andromeda's light is blue shifted, meaning it's moving toward us at about 110 kilometers per second, or roughly 223,694 miles per hour. But that's only the radial velocity, how fast it's moving directly toward or away from us. What about sideways motion? That's called proper motion, and it's incredibly difficult to measure for an object as distant as Andromeda. Here's why. Andromeda's sideways motion is less than 0.1 milliarcseconds per year. To put that in perspective, imagine trying to measure the rate of human hair growth from the distance of the moon. That's essentially what astronomers are attempting. They have to photograph thousands of stars in Andromeda, compare their positions to distant background galaxies that serve as fixed reference points, then wait years to see if those positions have shifted by amounts measured in billionths of a degree. The Hubble Space Telescope can do this, but barely. In 2002, Hubble photographed specific regions of Andromeda with extreme precision. In 2010, it photographed the same regions again. 8 years later, astronomers could measure tiny shifts in stellar positions and calculate Andromeda's proper motion. The result? Less than 200 kilometers per second of sideways velocity, much smaller than the approach speed. This suggested Andromeda was heading almost straight at us. But almost straight leaves room for uncertainty. Even a small sideways velocity, sustained over billions of years, can make the difference between a head-on collision and a near miss. Then there's mass. To predict how two galaxies will interact gravitationally, you need to know how massive they are. And here's the problem. Most of a galaxy's mass is invisible. It's dark matter, mysterious substance that doesn't emit light but exerts gravitational force. We can only infer dark matter's presence by measuring how it affects visible matter, by watching how stars orbit and how satellite galaxies move. For Andromeda, estimates of its total mass, including dark matter, range from about 800 billion to 1.5 trillion solar masses. That's a huge uncertainty range, and it matters. A more massive Andromeda exerts stronger gravitational pull, making collision more likely. A less massive Andromeda might not be able to capture the Milky Way gravitationally. And we can't forget about the other players in our cosmic neighborhood. The local group contains over 100 galaxies, most of them small, but a few are substantial enough to affect the dynamics of the Milky Way Andromeda system. The most important is the Large Magellanic Cloud, or LMC, a satellite galaxy orbiting the Milky Way. It contains only about 15% of the Milky Way's mass, but it's close enough that its gravitational influence matters. As the LMC orbits, it tugs on the Milky Way, slightly altering our galaxy's trajectory. And here's the crucial part. It pulls the Milky Way perpendicular to our orbital plane with Andromeda, potentially shifting us out of the direct collision path. Dr. Sawala explained, the LMC pulls the Milky Way off the orbital plane and away from Andromeda. It doesn't mean the LMC will save us from that merger, but it makes it a bit less likely. Then there's Triangulum, also called M33, the local group's third largest galaxy. It orbits Andromeda and adds its own gravitational complexity to the system. When the team included Triangulum in their simulations, the collision probability increased slightly, to about 67%. But when they added the LMC's effects, it dropped back down to 50%. The team accounted for 22 different variables in their simulations. Every uncertainty in position, velocity, and mass, every gravitational interaction between galaxies, every possible future trajectory. They ran 100,000 variations, creating a statistical portrait of possible futures. In just over half the simulations, the galaxies experience at least one close encounter within 8 to 10 billion years. They pass near each other, gravitational forces distorting both galaxies, triggering bursts of star formation. Then they loop back, approaching again, losing orbital energy with each pass until they finally merge into a single elliptical galaxy. This process takes billions of years, far longer than the original 4 to 5 billion year prediction. But in the other half of simulations, something different happens. The galaxies pass at such large distances that they continue evolving, largely unperturbed. They might exchange gravitational energy, they might pull at each other's outer halos, but they don't collide. They remain separate galaxies, continuing their independent journeys through space. The study authors were careful to emphasize that this doesn't mean previous predictions were wrong. Dr. Sawala noted, when we tried to start from the same assumptions as previous researchers, we recovered the same results. We've simply been able to explore a much larger space of possibilities, taking advantage of new data. The new conclusion is more honest about what we don't know. Previous studies had to make assumptions, choosing the most likely values for uncertain measurements. The new study accounts for all those uncertainties, running simulations across the full range of possible values. The result is less certain, but more accurate. Professor Carlos Frank from Durham University, a co-author of the study, put it bluntly, until now, we thought a merger was the fate that awaited our Milky Way galaxy. We now know that there is a very good chance that we may avoid that scary destiny. But there's another twist to this story. While the Milky Way Andromeda collision is now uncertain, a different collision has become almost certain. The study found that the Milky Way will almost definitely collide with the Large Magellanic Cloud within the next 2 billion years, long before any potential encounter with Andromeda. This LMC collision won't destroy the Milky Way, but it will change it profoundly. The merger will add mass to our galaxy, potentially feeding gas into the supermassive black hole at our galactic center and triggering a period of increased activity. It could disrupt star formation patterns, alter the structure of the galactic disk, and reshape the dark matter halo. Professor Frank explained, the merger between the Milky Way and the LMC will not destroy our galaxy, but it will change it profoundly, particularly impacting our central supermassive black hole and the galactic halo. So where does this leave us? The future is genuinely uncertain. Andromeda might collide with us in 8 to 10 billion years, reshaping both galaxies into something entirely new. Or it might pass by at a distance, leaving both galaxies largely intact to continue their separate evolutions. We won't know the answer definitively until we have better measurements. The Gaia spacecraft continues observing, building up longer time baselines that will refine our measurements of galactic motions. Future telescopes might be able to probe the dark matter distribution more precisely, reducing mass uncertainties. With each improvement in data, the range of possible futures will narrow. But for now, the collision remains a coin flip, 50-50, and there's something profoundly humbling about that uncertainty. Despite all our technology, despite all our understanding of physics and gravity and galactic dynamics, we cannot predict with certainty what will happen to our own galaxy billions of years from now. The universe is more complex than we imagined. Small uncertainties compound over vast timescales, turning precise predictions into probability distributions. The future is not written. It's a range of possibilities, and we exist in just one moment along one possible timeline. But here's what we do know. Whether or not the collision happens, Andromeda will continue to fascinate us. It will continue to reveal secrets about galaxy formation, stellar evolution, and the structure of the cosmos. And as we study it, we learn not just about Andromeda, but about ourselves, about the Milky Way, about the fundamental processes that shape all galaxies throughout the universe. The question now is, what else can Andromeda teach us? What secrets lie hidden in its vast structure? Let's venture deeper into the galaxy and confront one of the most mysterious objects in the cosmos. At the exact center of the Andromeda galaxy, hidden behind billions of stars, lurks a monster, an object so dense, so massive, so gravitationally powerful that nothing can escape it once it gets too close. Not light, not matter, not even space-time itself. It's a supermassive black hole, and it's called M31 star, or M31 asterisk. With a mass roughly 140 million times that of our Sun, M31 star is one of the most massive black holes in our cosmic neighborhood. To put that in perspective, if you could somehow weigh all the stars within 100 light-years of Earth, every star, every planet, every speck of matter, and multiply that mass by thousands, you still wouldn't reach the mass of Andromeda's central black hole. And yet, despite this almost incomprehensible mass, the black hole itself occupies a region smaller than the orbit of Mercury. All that mass, compressed into a volume that would fit comfortably inside our inner solar system. The density is beyond anything we can meaningfully visualize. If you could travel to the center of M31 star, which you absolutely cannot and should not, you would encounter a singularity, a point where all our theories of physics break down, where space and time become infinitely curved, where the very fabric of reality tears apart. But before you reach that singularity, you would cross the event horizon, the point of no return. This is the boundary of the black hole, the sphere beyond which escape is impossible. For M31 star, the event horizon has a radius of about 420 million kilometers. That's roughly 2.8 times the distance from Earth to the Sun. Think about that. An invisible sphere, nearly 3 astronomical units across, marking the boundary between the universe we know and a realm from which no information can ever return. Cross that boundary and you are gone. No signal you send, no light you emit, no cry for help you make will ever reach the outside universe. You have fallen out of causality itself. Supermassive black holes like M31 star are found at the centers of most large galaxies. The Milky Way has one too, called Sagittarius A star, but it's much smaller, only about 4 million solar masses. Why such a huge difference? Why is Andromeda's black hole over 35 times more massive than ours? The answer lies in Andromeda's violent history. Remember those galactic mergers we discussed? Each time Andromeda consumed a smaller galaxy, it didn't just absorb stars and gas. If that smaller galaxy had its own central black hole, and most galaxies do, then Andromeda's black hole absorbed that too. Black holes can merge, spiraling together over millions of years before finally combining in a cataclysmic collision that releases gravitational waves, ripples in space-time itself. Andromeda has eaten at least a dozen galaxies. That's at least a dozen black hole mergers. Each one added mass to the central monster, growing it larger and larger over billions of years. The black hole we see today is the accumulated result of Andromeda's entire cannibalistic history. But here's what's surprising. Despite its enormous mass, M31 star is relatively quiet. It's not actively feeding. It's not consuming massive amounts of material. It sits at the galaxy's center, exerting its gravitational influence, but producing very little radiation. This is unusual. Many supermassive black holes are surrounded by bright accretion disks, swirling vortexes of superheated gas, spiraling inward at nearly the speed of light. As gas falls toward a black hole, friction heats it to millions of degrees, causing it to emit intense X-rays and gamma rays. Some black holes power jets of plasma that shoot outward at relativistic speeds, visible across millions of light years. These active galactic nuclei, or AGN, can outshine their entire host galaxy. M31 star does none of this. it emits only faint X-ray and radio emissions. The black hole is essentially dormant, starving, surviving on the occasional star or gas cloud that wanders too close. Why? The most likely explanation is that Andromeda's central region has been cleared of gas. All the material that could easily fall into the black hole has already fallen. What remains is stars, orbiting at safe distances, and thin gas that doesn't efficiently feed the black hole. M31 star is in a quiescent phase, waiting for fresh fuel. This won't last forever. In a few billion years, if the Milky Way and Andromeda do collide, massive amounts of gas will be funneled toward the galactic center. The black hole will wake up, it will feast on this fresh material, heating an accretion disk to millions of degrees, potentially creating a luminous quasar that could be seen from billions of light years away. The two black holes, M31 star and our Sagittarius A star, will eventually spiral together and merge, releasing a burst of gravitational waves so powerful that future civilizations, if they exist, might detect it from across the universe, but that's billions of years away. For now, we can study M31 star in its dormant state, learning about the physics of supermassive black holes in their quieter moments. One of the most fascinating aspects of M31 star is its rotation. Black holes can spin, and M31 star is rotating at a significant fraction of the maximum possible rate. The rotation is measured by something called the spin parameter, which ranges from 0 for a non-rotating black hole to 1 for a black hole spinning at the theoretical maximum speed. M31 star has a spin parameter estimated between 0.84 and 0.96. That means it's rotating at close to the speed limit for black holes. Why does this matter? Because a spinning black hole drags space-time itself around with it, in a phenomenon called frame dragging, or the Lense-Thering effect. Imagine space-time as a fabric, which is a common but imperfect metaphor. Now imagine that fabric being twisted by the rotation of the black hole. Anything that enters this twisted region, even light itself, is forced to rotate in the same direction as the black hole. There's a region called the ergosphere, just outside the event horizon, where rotation is compulsory. You literally cannot remain stationary relative to the distant stars. The black hole's spin drags you along. This has profound effects on how matter falls into the black hole and how jets of plasma can be launched outward. It also affects gravitational waves emitted during black hole mergers. Understanding black hole spin is crucial for understanding black hole physics in general. Surrounding M31 star is a remarkable feature, a dense cluster of stars packed into a very small volume. Within just a few light years of the black hole, there are thousands of stars orbiting at incredible speeds. Some stars complete an orbit in just a few years, traveling at percentages of the speed of light. These stars are in an extreme environment. The gravitational field is so strong that Einstein's general relativity becomes important for calculating their orbits. Newtonian physics, which works perfectly fine for planets orbiting the Sun, breaks down here. Time flows differently depending on how close a star is to the black hole. Light is bent and distorted as it climbs out of the gravitational well. Observing these stars allows astronomers to test general relativity in conditions impossible to recreate on Earth. Every measurement confirms Einstein's century-old theory. Gravity behaves exactly as predicted, even in the most extreme environments we can observe. But M31 star is not the only black hole in Andromeda. Scattered throughout the galaxy are thousands, possibly millions, of smaller black holes. These stellar mass black holes form when massive stars, at least 20 times the mass of the Sun, exhaust their fuel and collapse. The collapse is catastrophic. In less than a second, the star's core implodes, compressing matter to densities beyond anything else in nature. If the core is massive enough, nothing can stop the collapse. It continues until a black hole forms. These stellar mass black holes, with masses ranging from a few to perhaps 100 solar masses, drift through the galaxy. Most are invisible, isolated, emitting no light. They're detectable only if they happen to be in a binary system with a normal star. Gas from the normal star can be pulled toward the black hole, forming a small accretion disk that emits X-rays. By observing these X-ray binaries, astronomers can map the population of stellar black holes in Andromeda. But the galaxy might also harbour intermediate mass black holes. with masses between 100 and 100,000 solar masses. These objects are rarer and more mysterious. They're too massive to form directly from a single star's collapse, but not massive enough to be supermassive black holes. How do they form? One possibility is that they form in dense star clusters. If a cluster is dense enough, stars can collide and merge, building up more and more massive objects. Eventually, these stellar mergers might produce a black hole that continues to grow by absorbing nearby stars. Over millions of years, an intermediate mass black hole could grow at the center of a globular cluster. Some of Andromeda's globular clusters might harbor such objects. Their presence would affect the motion of stars in the cluster, creating patterns that astronomers can detect. Finding these intermediate mass black holes would help solve the mystery of how supermassive black holes form. Perhaps they grow from intermediate mass seeds, gradually accumulating mass over billions of years. The future of M31 star is tied to Andromeda's future. If the galaxy continues evolving peacefully, the black hole will remain dormant, occasionally consuming a wandering star or gas cloud but producing little radiation. If Andromeda collides with the Milky Way, the black hole will feast, shine brilliantly for millions of years, then merge with our own black hole to create an even larger monster. Either way, M31 star will endure. Black holes are, as far as we know, eternal. They can grow but never shrink, at least not on timescales that matter. Billions of years from now, long after every star in both galaxies has burned out, long after the universe has expanded and cooled, M31 star will still be there, a frozen monument to Andromeda's violent past, waiting in the darkness. But there's something else in Andromeda that's even more mysterious than black holes. Something that makes up most of the galaxy's mass, yet remains completely invisible. It's time to talk about dark matter. If you could somehow see dark matter, Andromeda would look completely different. The bright spiral structure, the glowing core, the scattered stars, all of that would fade into insignificance. What you'd see instead is an enormous, roughly spherical cloud, stretching far beyond the visible galaxy, containing more mass than all the stars combined. This is Andromeda's dark matter halo, and it's one of the most profound mysteries in modern astrophysics. Dark matter makes up approximately 85% of Andromeda's total mass. That's not a typo. All the stars you see, all the gas and dust, all the planets and black holes and everything that emits or reflects light, that's only about 15% of what's actually there. The other 85% is invisible, detectable only through its gravitational effects. We've known about dark matter since the 1930s, when astronomer Fritz Zwicky noticed something odd about the Coma cluster of galaxies. The galaxies were moving too fast. Based on the visible mass, gravity shouldn't be strong enough to hold them together. They should fly apart, but they didn't. Zwicky proposed there must be some unseen mass, some dunkel materia or dark matter, providing extra gravity. But the real breakthrough came in the 1960s and 70s, thanks to astronomer Vera Rubin. She studied Andromeda and measured how fast stars orbit at different distances from the galactic center. In a normal system, objects farther from the center should orbit more slowly, just like planets in our solar system. Mercury zips around the sun quickly, while Neptune crawls along at a much slower pace. But Andromeda doesn't behave this way. Rubin found that stars in the outer regions of the galaxy orbit just as fast as stars near the center. The rotation curve, as it's called, stays flat instead of dropping off. This was completely unexpected and profoundly important. There's only one explanation. There must be additional mass spread throughout and beyond the visible galaxy, providing extra gravitational pull. This invisible mass keeps the outer stars moving fast, preventing them from drifting away. When astronomers calculated how much dark matter was needed to explain the flat rotation curve, the answer was shocking. The dark matter halo must extend far beyond the visible galaxy and contain several times more mass than all the stars combined. Rubin's work on Andromeda provided some of the earliest and most convincing evidence for dark matter. In recognition of her groundbreaking contributions, the United States Mint released a quarter in 2025 featuring Vera Rubin as part of the American Women Quarters program. She's the first astronomer honored in the series. a fitting tribute to someone who revealed that the universe is far stranger than we'd imagined. Since Rubin's time, dark matter has become central to our understanding of galaxies. Without it, galaxies couldn't form in the first place. In the early universe, shortly after the Big Bang, matter was spread almost uniformly through space. Tiny density fluctuations, quantum ripples from the first moments of existence, provided the seeds for structure formation. Regions slightly denser than average began attracting matter gravitationally, growing denser over time. But this process wouldn't work with normal matter alone. Normal matter, also called baryonic matter, interacts with light and can be slowed down by radiation pressure. In the early universe, radiation was intense, and baryonic matter couldn't collapse efficiently. Dark matter, however, doesn't interact with light. It's immune to radiation pressure. So dark matter started collapsing first, forming gravitational wells that eventually pulled in baryonic matter. Over hundreds of millions of years, these dark matter clumps grew into halos, vast structures that served as scaffolds for galaxy formation. Gas fell into these halos, compressed, fragmented, and began forming stars. The galaxies we see today, including Andromeda, are essentially baryonic icing on a dark matter cake. Andromeda's dark matter halo extends out to at least 500,000 light-years from the galactic center, possibly much farther. It's roughly spherical, though observations suggest it might be slightly elongated or lopsided, shaped by past collisions with satellite galaxies. The halo's mass is estimated between 800 billion and 1.5 trillion solar masses, with most of that being dark matter. The distribution isn't uniform. Dark matter is densest near the galactic center and gradually thins out with distance. Computer simulations suggest the halo should have substructure, clumps of dark matter called subhalos, that represent the remnants of smaller halos that merged to form Andromeda's main halo. These subhalos might still be lurking in the outer regions, affecting the orbits of satellite, galaxies, and streams of stars. One way to search for dark matter subhalos is to look for their gravitational effects on stellar streams. When a dwarf galaxy is torn apart by Andromeda's gravity, its stars form long streams that orbit the main galaxy. These streams are very thin and sensitive to gravitational disturbances. If a dark matter clump passes near a stream, it creates a gap, a region where stars are missing or have been scattered. By mapping these gaps, astronomers can indirectly detect dark matter structures. The Nancy Grace Roman Space Telescope, scheduled to launch by May 2027, will be instrumental in this search. Its wide field of view and sensitive instruments will allow it to map stellar streams throughout Andromeda's halo in unprecedented detail. Astronomers are expecting to find evidence of dozens or even hundreds of dark matter subhalos, each one a piece of the puzzle of how galaxies form and evolve. But what is dark matter made of? After decades of research, we still don't know. The leading theory is that it's composed of weakly interacting massive particles, or WIMPs. These hypothetical particles would have mass, but interact with normal matter only through gravity and possibly the weak nuclear force. They would pass through ordinary matter like ghosts, making them nearly impossible to detect directly. Experiments around the world are searching for WIMPs. Underground laboratories use ultra-sensitive detectors, hoping to catch the rare occasion when a dark matter particle collides with an atomic nucleus. So far, these experiments have found nothing, pushing the possible mass and interaction strength of WIMPs into increasingly constrained ranges. Other theories suggest dark matter might be axions, incredibly light particles predicted by certain extensions of particle physics. Or it could be primordial black holes, tiny black holes formed in the first moments after the Big Bang. Or it could be something completely unexpected, something our current physics hasn't even predicted. The mystery of dark matter's composition remains one of the great unsolved problems in science. But regardless of what it's made of, dark matter's effects are undeniable. It shapes galaxies, determines their rotation, holds them together, and provides the gravitational framework for all structure in the universe. And when Andromeda and the Milky Way interact, whether through collision or close encounter, their dark matter halos will play a crucial role. The halos will interpenetrate, passing through each other since dark matter doesn't collide in the same way normal matter does. but their gravitational influence will reshape both galaxies, determining the outcome of the encounter. Understanding Andromeda's dark matter distribution is essential for predicting our galactic future. It's also essential for understanding the universe itself. Every advance in mapping dark matter in Andromeda brings us closer to solving one of cosmology's deepest mysteries. And as we continue to explore Andromeda's structure, we find that dark matter is just one of many invisible components that make the galaxy far more complex than it appears. And as we continue to explore Andromeda's structure, we find that dark matter is just one of many invisible components that make the galaxy far more complex than it appears. But while the invisible dominates by mass, it's the visible companions, the swarm of smaller galaxies orbiting Andromeda, that tell us the most dramatic stories. Imagine standing outside on a clear night, looking up at Andromeda. That faint smudge appears alone, solitary, drifting through space. But if you could somehow see the complete picture, what you'd actually witness is something far more dynamic. Andromeda isn't alone. It's the center of a bustling galactic ecosystem, surrounded by a swarm of nearly 36 smaller galaxies, each one orbiting like moons around a planet. These are Andromeda's satellite galaxies, and they're revealing secrets that challenge everything we thought we knew about how the universe works. In February 2025, NASA's Hubble Space Telescope completed an extraordinary survey using over 1,000 Hubble orbits to study 36 dwarf satellite galaxies circling Andromeda. This wasn't just photography, it was forensic archaeology, using light to reconstruct billions of years of history. What the team discovered was startling. Andromeda's satellite galaxy ecosystem has had a more dynamic history than the Milky Way, likely affected by a major merger with another big galaxy a few billion years ago. This violence explains why Andromeda has so many satellites compared to our own galaxy's more modest collection. But here's where it gets truly strange. These satellite galaxies aren't arranged the way they should be. According to the standard model of cosmology, satellite galaxies should be scattered roughly randomly around their host, like bees buzzing around a hive. Dark matter simulations predict this. The math demands it. Every computer model shows the same thing. Satellites orbiting in all directions, filling a spherical cloud around the massive galaxy. Andromeda's satellites completely defy this prediction. Instead of being randomly distributed, over 80% of Andromeda's dwarf galaxies are concentrated on one side of the galaxy, with all but one of Andromeda's satellites lying within 107 degrees of the line pointing toward the Milky Way. This asymmetry is so extreme that when researchers at the Leibniz Institute for Astrophysics, Potsdam, ran simulations to see how rare this configuration might be, the answer was shocking. Less than 0.3% of simulated galaxy systems show a comparable asymmetry, meaning you'd have to look at more than 300 simulated systems to find just one that is similarly extreme. Andromeda is a statistical outlier, an anomaly that shouldn't exist in our current understanding of cosmology. But wait, it gets stranger. About half of Andromeda's satellites don't just cluster on one side. They orbit in a thin, flat plane, like planets around a star. This structure, called the Great Plane of Andromeda, has been observed for over a decade, and it persists even as new satellites are discovered. The galaxies in this plane move in the same direction, co-rotating with remarkable coherence. This shouldn't happen, ever. In the standard cosmological model, such organized motion is virtually impossible for satellite galaxies that supposedly formed from random collisions and chaotic mergers over billions of years. Dr. Marcel Pawlowski from the Leibniz Institute for Astrophysics explained the significance. The coexistence of a plane of satellite galaxies and a lopsided satellite distribution is highly unexpected in the standard cosmological model. The Milky Way has a similar plane of satellites, also unexplained. A galaxy called Centaurus A shows the same structure. This isn't just an Andromeda problem, it's becoming a pattern, and patterns demand explanations. Several theories have been proposed, but none are entirely satisfying. One hypothesis suggests that the major merger Andromeda experienced 2 to 3 billion years ago may have been responsible, with many satellites falling in recently due to this event. Perhaps the merger somehow funneled dwarf galaxies into specific orbits, creating the plane we see today. Another idea invokes cosmic filaments, the vast threads of dark matter and gas that connect galaxies across the universe. Maybe Andromeda's satellites are being fed through one such filament, all arriving from the same direction. But this fails to explain the co-rotating plane. The most unsettling explanation for cosmologists is that our simulations are simply missing something fundamental. Perhaps stellar feedback, dark matter interactions, or even unknown physics needs to be incorporated to reproduce these anomalies. If so, our understanding of galaxy formation at small scales may need a complete overhaul. Let's look at some of these satellite galaxies individually, because each one has its own story. Start with Messier 32, or M32 for short. It's the brightest of Andromeda's satellites, easily visible through a basic telescope, orbiting just 24,000 light-years from Andromeda's core. M32 is a compact elliptical galaxy, incredibly dense, packed with stars. But something about M32 has always bothered astronomers. It's far too small for its density. Computer simulations suggest M32 was once much larger, possibly a spiral galaxy in its own right, before getting too close to Andromeda and having its outer layers stripped away by tidal forces. What we see today is essentially a galactic ghost, the compressed core of what was once a much grander system. M32 experienced a big burst of star formation a few billion years ago, and star formation continued at a slower rate for much longer than expected. This is puzzling. Galaxies this close to a massive host should have had their gas stripped away long ago, ending star formation. Yet M32 kept forming stars, suggesting it somehow held onto gas reserves or captured new material during its death spiral. Then there's Messier 110, or M110, Andromeda's second brightest satellite. It orbits farther out than M32 and appears to be interacting with Andromeda more gently. M110 contains a dusty lane, which may indicate recent or ongoing star formation. Astronomers have found streams of metal-rich stars stripped from M110 and scattered into Andromeda's halo, evidence of ongoing tidal disruption. Both M32 and M110 are visible deaths in progress, slowly being consumed by Andromeda's relentless gravity. And then there are the truly faint satellites, galaxies so dim they were only discovered in the past few decades as telescopes became sensitive enough to detect them. These ultra-faint dwarfs are fossils from the early universe, ancient systems that somehow survived 13 billion years largely unchanged. Many of these faint satellites appear to have been quenched, stripped of their gas and shut down from star formation long before they actually fell into Andromeda's gravitational grip. Researchers found that the majority of lower mass satellites were quenched significantly before their first close passage with Andromeda, with some quenched up to 10 billion years ago. How? One mechanism is reionization, when ultraviolet radiation from the first stars heated gas throughout the universe, giving it enough energy to escape from low-mass galaxies. Another process is pre-processing, where a satellite spent time near a different, smaller host galaxy before eventually falling toward Andromeda. This earlier interaction could have removed gas and quenched star formation billions of years ago. The faintest satellites tell us about conditions in the early universe. They formed when the cosmos was young, when heavy elements were rare, and they've been drifting through space ever since, slowly falling into the gravitational wells of larger galaxies. Pegasus 7, discovered in February 2025, is one of these ancient wanderers. It's one of the faintest Andromeda satellites ever detected, with a stellar mass of only 26,000 solar masses, and it's roughly 10 billion years old. For most of cosmic history, Pegasus 7 drifted freely through intergalactic space, but now it's entering Andromeda's domain, and its fate is sealed. Over the next few billion years, gravity will pull it inward, stretch it, tear it apart, and scatter its stars across Andromeda's halo. We're watching galactic cannibalism in real time. The Hubble survey revealed something else unexpected. Star formation in Andromeda's satellite galaxies continued much longer than astronomers assumed, lasting for almost the entire age of the universe. This contradicts theoretical predictions. Small galaxies should run out of gas quickly. They should be quenched early. Yet many satellites kept forming stars for billions of years longer than expected. Alessandro Savino, the lead researcher, explained, "The duration for which satellites can continue forming new stars really depends on how massive they are and how close they are to Andromeda. indicating how small galaxy growth is disturbed by the influence of a massive galaxy. This tells us that satellite evolution isn't simple. It's not just about size or distance. It's about timing, orbital paths, gas content, and the complex interplay between a dwarf galaxy trying to form stars and a massive host galaxy trying to strip away its fuel. The team plans to observe these satellites again in about 5 years, using either Hubble or the James Webb Space Telescope. By comparing images taken years apart, they'll be able to measure how the satellites are moving, reconstructing their orbits backwards in time to understand how they arrived in their current positions. This work will help determine whether Andromeda's bizarre satellite configuration is truly unique or if similar systems exist elsewhere in the universe. The European Space Agency's Euclid mission, currently surveying vast regions of sky, will search for comparable asymmetries around other galaxies. If Andromeda turns out to be common rather than rare, that would be even more troubling for cosmology. It would suggest our simulations aren't just missing one galaxy's peculiarities, they're missing something fundamental about how galaxies assemble their satellite systems. The satellite galaxies of Andromeda are more than just pretty companions. They're forensic evidence, each one a clue to the galaxy's violent past. They record mergers, collisions, and near misses. They trace the flow of dark matter through intergalactic space. They challenge our theories and force us to confront the limits of our understanding. And they remind us that even after 100 years of studying Andromeda, the galaxy still holds secrets we're only beginning to unravel. If satellite galaxies are Andromeda's companions, then globular clusters are its time capsules. Scattered throughout the galaxy, orbiting in the halo and disk, are approximately 500 globular clusters, dense, ancient collections of stars that have survived since the galaxy's youth. Andromeda hosts approximately 500 globular clusters, nearly twice the number in the Milky Way. These aren't just any star clusters. They're survivors from the galaxy's formation, each one containing hundreds of thousands to millions of stars packed into a region just tens of light years across. The most spectacular of these is Male 2, also called Globular 1 or simply G1. Male 2 is the brightest globular cluster in the local group, with an absolute visual magnitude of -10.94 and the luminosity of 2 million suns, considered to have twice the mass of Omega Centauri. To put that in perspective, Omega Centauri is the largest globular cluster in the Milky Way, visible to the naked eye from the southern hemisphere, containing about 10 million stars. Male 2 is twice as massive. It's so large and luminous that some astronomers don't think it's a globular cluster at all. Because of the widespread distribution of metallicity indicating multiple star generations, some consider Male 2 to be the remnant core of a dwarf galaxy consumed by Andromeda in the distant past. This makes sense. If Andromeda has been eating smaller galaxies for billions of years, and if those galaxies had their own central star clusters, then some of those clusters would survive the merger, becoming incorporated into Andromeda's system. Male 2 might be exactly this, the indestructible heart of a long-dead galaxy. Globular clusters are valuable because they contain simple stellar populations, stars that all formed at roughly the same time from the same gas cloud. By studying a cluster's stars, astronomers can determine its age, its chemical composition, and the conditions that existed when it formed. Andromeda's globular clusters reveal two distinct kinematic populations with rotation axes perpendicular to each other. This is extraordinary. It means that one population of clusters orbits Andromeda in one plane, while a completely different population orbits perpendicular to it. These two populations must have come from separate sources, likely from two major merger events that occurred billions of years apart. One population probably formed within Andromeda itself, or was accreted during the galaxy's early assembly. The other population likely came from a massive galaxy that Andromeda consumed later in its history. The perpendicular rotation preserves the orbital signature of that ancient collision. Globular clusters also show us Andromeda's chemical evolution. Clusters in the galaxy's core are metal poor, containing fewer heavy elements. These are the oldest clusters, born when the universe was young and only hydrogen and helium were abundant. Clusters in the disk and outer halo show higher metallicities, enriched by supernova explosions that scattered heavy elements into space. The radial distribution and kinematics of Andromeda's metallicity groups suggest they are analogues of the galactic halo and disk bulge cluster systems. This tells us that despite Andromeda's more violent history, it formed its globular cluster system through similar processes as the Milky Way: early collapse and halo formation, followed by gradual disk assembly. But there are differences. The best fit models for metal-rich clusters are younger than those for metal-poor ones, suggesting that Andromeda experienced a late burst of cluster formation, possibly triggered by the major merger 2 to 3 billion years ago. Some globular clusters in Andromeda might harbour intermediate mass black holes, objects with masses between 100 and 100,000 solar masses. These are the missing link between stellar mass black holes and supermassive black holes, and we don't fully understand how they form. Finding them in globular clusters would help solve this mystery. Then there are the stellar streams, long, faint rivers of stars stretched across Andromeda's halo. These are the graveyards of dwarf galaxies, the scattered remains of satellites that ventured too close and paid the ultimate price. When a dwarf galaxy approaches Andromeda, tidal forces stretch it. Stars on the side closer to Andromeda feel stronger gravity than stars on the far side. This differential pull tidal force distorts the galaxy, pulling it into an elongated shape. Eventually, the galaxy is torn apart completely, its stars scattered along its orbital path. What remains is a stellar stream, a thin line of stars all moving together, all sharing the same origin. These streams trace the orbits of dead galaxies, preserved in the motions of their scattered stars. The Hubble images show these streams clearly, long arcs stretching across the outer galaxy, some bright and well-defined, others so faint they're barely detectable. Each stream is a fossil, evidence of a merger that happened millions or billions of years ago. By mapping these streams and modelling their orbits, astronomers can reconstruct Andromeda's merger history. How many galaxies has it consumed? When did the mergers occur? Where did the satellites come from? The streams hold the answers. And here's something fascinating. Some streams show gaps, regions where stars are missing. These gaps are evidence of dark matter subhalos passing through the stream and gravitationally perturbing it. By studying these gaps, astronomers can map dark matter structures that are otherwise completely invisible. The Nancy Grace Roman Space Telescope, scheduled to launch by May 2027, will revolutionize this field. Its wide field of view will allow it to map stellar streams throughout Andromeda's halo in unprecedented detail, potentially discovering hundreds of dark matter subhalos and revealing the complete history of Andromeda's assembly. But stellar populations aren't just about the past. They also tell us about star formation happening right now. Scattered throughout Andromeda's spiral arms are star-forming regions, massive clouds of gas and dust where new stars are being born. These regions glow blue in ultraviolet light, radiating the intense energy of young, massive stars. The Hubble survey captured many of these regions, revealing that Andromeda is actively forming stars at a significant rate. This is somewhat surprising. Andromeda is an old galaxy. It should have used up most of its star-forming gas by now, but the mergers it's experienced brought in fresh fuel. Each time Andromeda consumed a smaller galaxy, it gained new gas reserves, triggering bursts of star formation that continue to this day. The youngest stars in Andromeda are only a few million years old, cosmic infants still surrounded by the gas clouds from which they formed. These stars will live for millions or billions of years, shining brightly before eventually dying and returning their enriched material to the interstellar medium, fueling yet another generation of stars. And then there are the variable stars, cosmic lighthouses whose brightness changes over time. Cepheid variables, the same stars Edwin Hubble used to measure Andromeda's distance, pulsate with clockwork regularity. RR Lyrae variables, older and fainter, pulsate more rapidly. Long-period variables swell and shrink over months or years. These variables are scattered throughout Andromeda, and astronomers use them to measure distances within the galaxy, map its three-dimensional structure, and study stellar evolution. Each variable star is a natural laboratory, showing us how stars behave as they age and evolve. The complete picture of Andromeda's stellar populations is one of incredible diversity. Ancient metal-poor stars from the galaxy's birth, younger metal-rich stars formed during recent mergers, globular clusters preserving records of multiple accretion events, stellar streams tracing the deaths of dwarf galaxies, active star formation continuing in spiral arms, variable stars pulsating across the galaxy. All of this complexity, all of this history, encoded in light, and we're only beginning to read it. For decades, the story seemed written. Andromeda and the Milky Way were on a collision course. In roughly 4 to 5 billion years, they would smash together in a cosmic train wreck that would reshape our entire corner of the universe. The merger would create Andromeda, a giant elliptical galaxy, and our sun would be flung to the outer suburbs or possibly ejected entirely into intergalactic space. This was the consensus. It was in textbooks. It was in planetarium shows. It was presented as cosmic certainty. But as we've already explored, June 2025 changed everything. The 50-50 odds of collision left the future genuinely uncertain, but let's dig deeper into what would actually happen in each scenario. First, let's explore the collision scenario. What happens if those 50-50 odds land on yes? The encounter wouldn't be sudden. Researchers found the galaxies would experience at least one close encounter within 8 to 10 billion years, passing near each other with gravitational forces distorting both galaxies before looping back and approaching again. This isn't a one-time smash. It's a slow dance that takes billions of years. The first close passage would occur roughly 4 billion years from now. At that point, Andromeda would dominate Earth's night sky if anyone was around to see it. The galaxy would stretch across the heavens, a luminous band far more spectacular than the Milky Way appears today. But let's be clear, Earth won't be around to witness this. Earth will be uninhabitable due to increased solar luminosity long before the galactic merger occurs. The sun is gradually getting brighter as it ages. In about 1 billion years, the sun's increased luminosity will trigger a runaway greenhouse effect, boiling away Earth's oceans and making the planet uninhabitable. By the time the galaxies collide, Earth will be a dead, scorched rock orbiting a sun that's beginning to swell into a red giant. But let's imagine future observers, perhaps on a world in the outer solar system or aboard a spacecraft. What would they see? At 3.75 billion years from now, Andromeda and the Milky Way prepare for their initial collision, with Andromeda filling much of the field of view. The two galaxies would pass through each other, not colliding star to star. The distances between stars are too vast for that, but interpenetrating, their stars passing like ghosts through fog. But the gas wouldn't pass so cleanly. The thin disk shapes of the spiral galaxies would be strongly distorted and irrevocably transformed by the encounter, with gas clouds compressing and triggering massive bursts of star formation. The collision would ignite stellar nurseries on a scale unprecedented in either galaxy's recent history. At 3.85 billion years, the sky would brighten from the emergence of newly formed stars. The galaxies would separate after the first pass, but gravity would pull them back together. At 4 billion years, the Milky Way would appear warped and Andromeda stretched following their first encounter. Over the next few billion years, they would approach again, each passage stripping away gas, flinging stars into new orbits, and losing orbital energy to gravitational interactions. At 5.1 billion years, the cores of the Milky Way and Andromeda would appear as a pair of bright lobes. Finally, at 7 billion years, the two galaxies would combine to form a huge elliptical galaxy. The result? Andromeda. Andromeda would be a giant elliptical galaxy, but with a center showing less stellar density than current elliptical galaxies. This is because Andromeda and the Milky Way don't have enormous gas reservoirs at their cores. When gas-rich galaxies merge, the collision funnels vast amounts of gas to the center, triggering a nuclear starburst that creates a dense stellar core. Our merger won't have enough gas for that. Andromeda will be more diffuse, less centrally concentrated than typical ellipticals. The merger would also affect the supermassive black holes. The supermassive black holes at the centers of the Milky Way and Andromeda would converge near the center of the newly formed galaxy over millions of years through dynamical friction, eventually coming within 1 light year of each other and beginning to strongly emit gravitational waves. Astronomers estimate the galaxies would coalesce into one giant elliptical galaxy in about 10 billion years. Then the central black holes would begin orbiting one another and finally collide less than 17 million years later. Just before merging, They'd radiate gravitational waves with the power of 10 quintillion suns, creating ripples in space-time that would be detectable across the universe. The merged black hole would be enormous, about 144 million solar masses, making it one of the most massive black holes in the local universe. It might briefly become an active galactic nucleus, shining as a quasar as it consumes the gas funneled toward it during the merger. But what about our solar system? The odds aren't great for staying in our current neighborhood. Modeling suggests a 50% probability that the solar system will be displaced 3 times its current distance from the galactic core, and a 12% chance of ejection into intergalactic space. Currently, we orbit about 26,000 light-years from the Milky Way's center. If displaced, we'd end up roughly 78,000 light-years from the center of Andromeda, in the outer suburbs where stars are sparse and the galaxy appears as a distant glow. If ejected entirely, we drift through the void between galaxies, truly alone in the darkness. No galactic center to orbit, no spiral arms, no stellar neighborhood. Just our sun, its planets, and an empty cosmos stretching in all directions. But here's the strange comfort. Collisions between individual stars or planets are extremely rare during galaxy mergers, because the distances between stars are too vast. Our sun won't hit another star. Earth won't collide with another planet. The gravitational chaos will alter our orbit, but the solar system itself will remain intact. Of course, by then the sun will be approaching the end of its life, regardless of galactic position. The sun will still be a main sequence star during the merger, although reaching the end of its core hydrogen burning phase. Within another billion years after the merger, the sun will expand into a red giant, consuming Mercury and Venus and possibly Earth. That's the collision scenario. But what if the galaxies miss? In the non-collision scenario, which now appears equally probable, the galaxies would pass at a safe distance. They'd still interact gravitationally. They might exchange stars at their outer edges. They'd definitely disturb each other's satellite systems, but they wouldn't merge. Both galaxies would continue their separate evolutions. The Milky Way would remain a spiral. Andromeda would remain a spiral. Our sun would stay in its current orbit, following its natural life cycle without galactic disruption. This doesn't mean we're safe forever. The study found that the Milky Way will almost definitely collide with the Large Magellanic Cloud within the next 2 billion years, long before any potential Andromeda encounter. The Large Magellanic Cloud is a satellite galaxy of the Milky Way, currently about 160,000 light-years away, containing roughly 1/10 of the Milky Way's mass. When the LMC collides with the Milky Way, it won't destroy our galaxy, but it will change it profoundly. The merger would add mass to our galaxy, potentially feeding gas into the supermassive black hole at the galactic center and triggering increased activity. It could disrupt star formation patterns and reshape the dark matter halo, so even if we avoid Andromeda, we're not avoiding galactic disruption entirely. And there's one more long-term certainty worth considering. All galaxies not bound to the local group will eventually recede away due to the accelerated expansion caused by the cosmological constant and exit our event horizon. In roughly 100 billion years, everything beyond the local group will have been carried so far away by cosmic expansion that its light will never reach us again. At that point, whether Milkomeda exists or whether the Milky Way and Andromeda remain separate, the local group will constitute the entire observable universe. Future astronomers, if they exist, won't even know other galaxies existed. The universe will appear to be just one galaxy, or a few, floating in infinite darkness. That's our ultimate cosmic fate. Not a collision, not destruction, isolation. But we won't be there to see it. The sun will be long dead. The earth will be gone. Humanity, if it survives, will have spread to other stars, other systems, perhaps even other galaxies, while travel was still possible. And those distant descendants will face their own cosmic questions, their own uncertainties, their own searches for meaning in an ever-expanding universe. We've travelled 2.5 million light-years across intergalactic space. We've witnessed the birth of stars in stellar nurseries hidden behind cosmic dust. We've explored the violent history that shaped Andromeda into what it is today. We've confronted the supermassive black hole at its heart, orbited by thousands of stars moving at percentages of light speed. We've traced dark matter's invisible empire. We've examined the chaotic satellite system that defies cosmological predictions. We've studied globular clusters and stellar streams that preserve records of ancient mergers. And we've peered into multiple possible futures, each one uncertain, each one profound. This is what Andromeda has taught us. But the lessons extend far beyond one galaxy. They're lessons about the universe itself, about how structure forms, how galaxies grow, how matter behaves under extreme conditions. They're lessons about time and scale, about forces so vast they bend space-time, and processes so slow they take billions of years to unfold. Every fact we've explored in this journey has been verified against the latest 2025 research. The 2.5 billion pixel Hubble mosaic released in January, the June collision simulations showing 50% odds, the February discovery of Pegasus 7, the April findings about Andromeda's asymmetric satellites, challenging cosmology, the ongoing Hubble survey of satellite galaxy star formation. All of it is real. All of it is happening right now, this moment, as photons travel across space to reach our telescopes. Think about that. The light entering our instruments tonight left Andromeda 2.5 million years ago. When those photons began their journey, our ancestors Homo habilis were just learning to use stone tools. The entire history of human civilization, writing, cities, science, space exploration has unfolded in the time it took that light to reach us. We are seeing the past, always. There is no now for Andromeda as we observe it. What we see is ancient history, frozen in light. Andromeda as it appeared when ice ages gripped our planet, when our species didn't yet exist, when Earth was a world of primitive hominids struggling to survive on the African plains. And what's happening in Andromeda right now, at this actual moment, we won't know for another 2.5 million years. Stars being born today in Andromeda's spiral arms, their light won't reach Earth until our descendants, if they exist, witness it. This is the strange nature of cosmic observation. We're time travelers, always looking backward, never able to see the present moment of distant objects. But there's something profound in that limitation. It means the universe preserves its history for us. Every photon is a message, a piece of information about how things were. By studying those messages, we can reconstruct the past, understand the present, and predict the future. And what does Andromeda's future hold? We genuinely don't know. 50-50 odds of collision. Coin flip. Even with the most advanced telescopes, the most sophisticated simulations, the most precise measurements, we cannot say with certainty what will happen to our galaxy billions of years from now. There's something humbling in that uncertainty. Despite all our technology, despite all our understanding of physics, the future remains open. Multiple timelines exist simultaneously in possibility space, and we won't know which one becomes reality until it happens. But here's what we do know. Andromeda will continue to fascinate us. Every improvement in observational technology reveals new details, new mysteries, new questions. The James Webb Space Telescope is just beginning its observations of Andromeda, capturing infrared light that penetrates dust clouds to reveal hidden star formation. The Nancy Grace Roman Space Telescope will map stellar streams in unprecedented detail. Future gravitational wave detectors might pick up signals from black hole mergers in Andromeda, giving us entirely new ways to study the galaxy. Each advance brings us closer to understanding not just Andromeda, but galaxies in general. The processes that shaped Andromeda hierarchical assembly, dark matter halos, galactic cannibalism, supermassive black holes, stellar population, evolution, these are universal. They apply to every large galaxy in the cosmos. By understanding Andromeda, we understand the mechanisms that created all galactic structures throughout the universe. And there's something else worth considering. In all those trillion stars, orbited by countless planets, what are the odds we're alone? If even a tiny fraction of those worlds harbour life, then Andromeda contains billions of living worlds. Perhaps some host intelligent civilizations, beings who look up at their night sky and see a faint smudge they call the Milky Way, wondering if anyone is out there, asking the same questions we ask. We may never know. Andromeda is simply too far for communication or travel with any technology we can currently imagine. but the possibility exists. And that possibility expands our perspective, reminds us that we're part of something incomprehensibly vast, a universe teeming with potential and mystery. This is why we study Andromeda. Not just to gather data, not just to test theories, but to understand our place in the cosmos, to know where we came from, where we're going, what forces shaped us and continue to shape us, to feel that sense of wonder that comes from confronting the infinite. Our galaxy and Andromeda might collide, reshaping our corner of the universe into something entirely new. Or they might pass safely by, continuing their separate journeys through space. Either way, the story continues. Stars will be born, stars will die, black holes will grow, dark matter will hold everything together, and somewhere, somehow, observers will look up at the sky and try to make sense of it all. That's our cosmic story. Not fixed, not predetermined, open-ended, uncertain, magnificent in its complexity and scale. And you, by taking this journey with us, by spending 2 hours exploring the depths of Andromeda, have become part of that story. You've looked across intergalactic space, witnessed galactic violence, confronted cosmic mysteries, and contemplated futures that won't arrive for billions of years. You've seen what's out there. You've understood, if only briefly, the scale of it all. The Andromeda galaxy will still be there tomorrow night. That same faint smudge, barely visible to the naked eye, carrying light from 2.5 million years ago. Most people will pass under it without noticing, but you know what it is now. You know its history, its structure, its possible futures. You know the trillion stars it contains, the supermassive black hole at its core, the dark matter holding it together, the satellite galaxies spiraling toward their doom. That knowledge changes how you see the sky. It changes how you think about distance, time, and scale. It changes what it means to be human in a universe so vast that our entire existence is less than a cosmic blink. And that's the real gift of astronomy. Not just facts and figures, but perspective. The understanding that we're part of something much larger than ourselves, much grander, much more complex and beautiful than we could ever imagine. So go outside tonight, look up, find that faint smudge in Andromeda, let your eyes adjust to the darkness. And remember, you're seeing ancient light from a galaxy of 1 trillion suns, a cosmic empire whose fate is intertwined with our own, a neighbour in the vast darkness of space. Thank you for joining us on this journey. The universe is full of wonders waiting to be explored, mysteries waiting to be solved, stories waiting to be told. We're just getting started. Until next time, keep looking up, keep wondering, keep exploring. The cosmos is calling, and the adventure never ends. Clear skies, everyone.